This is Chapter 15, Lecture number 2. We're going to discuss calorimetry. Calorimetry problems are solved exactly like the problems from yesterday's lecture, in that we are going to substitute into the equation Q equals mc delta T. The difference is that instead of looking at just the object, we are going to place an object into a cup of water. And we're going to measure not the object, but the water that it was placed into. So calorimetry uses the same formula. Q, or joules, is equal to, but this time, the mass of the water in the calorimeter times the specific heat of water, which we can find in table B, and the change in temperature of the water. So we don't need to know anything about the object. We just need to know about the water in the coffee cup. The reason this works is conservation of energy. The energy that's given off by the object when it is placed in the water is absorbed by the water. So whatever the water absorbs, it came from the object that was given off. So for example, here is a calorimeter in picture A. In picture B, we're adding a hot piece of metal. And in picture C, we're seeing what happens to the difference in temperature. So to solve this problem, we need to know all of the information about the water. So Q is equal to the mass of the water, 125 grams, the specific heat of water from table B, 4.18 joules per gram degree Celsius, and we need to know the change in temperature of the water, not the metal, the water. So the final temperature, 29.30, minus the initial temperature, 25.60, means there's a difference of 3.70 degrees Celsius. So Q, the energy absorbed, is 1,933.25 joules, but to 3 sig figs would be 1,930 joules. The next topic is called thermochemistry, and it deals with heat changes. By heat changes, we mean when a chemical reaction occurs, energy will either leave the system or it will enter the system. The system is what we're focusing on, and everything else is called the surroundings. So everything else in the universe. We have a term called enthalpy. Enthalpy is the measure of the energy change. In order to measure enthalpy, delta H is equal to the delta H of the products minus the delta H of the reactants. So products minus reactants. We have to remember that. In an exothermic reaction, we have a process that releases energy. The system is losing energy. So a campfire releases energy to the surroundings. Freezing releases energy to the surroundings. Freezing is an exothermic reaction. We represent an exothermic reaction with a diagram. Here's our reactants, here's our product. Delta H is products minus reactants, the heat of the products minus the heat of the reactants. So in this case, we have a small value minus a large value. Small minus large will give us a negative number. So in an exothermic reaction, delta H is negative. In an exothermic reaction, the energy term is written to the right of the arrow. So we sum it up by saying in an exothermic reaction, the sign of delta H is negative, and in an exothermic reaction, the energy term is on the right side of the equation. So here we have an example. We know this reaction is exothermic because the energy term is to the right of the arrow. And because it's an exothermic reaction, the value for delta H is 198 kilojoules, but because it's exothermic, we put a negative sign in front. The negative sign just means exothermic. So we can probably then figure out an endothermic reaction. An endothermic reaction is a process that absorbs heat from the surroundings. Now, here's our reactants. They absorb energy to turn into products. Delta H, products minus reactants, a large value minus a small value will give us a positive value. So in an endothermic reaction, delta H is positive. In an endothermic reaction, the energy term is left of the arrow. So in an endothermic reaction, the sign of delta H is positive. In an endothermic reaction, the energy term is on the left side of an equation. So here we have a thermochemical equation. This reaction is endothermic because the energy term is left of the arrow, and the value for delta H is 198 kilojoules, and since it's an endothermic reaction, it's a positive 198 kilojoules. If we look at table I in the reference table, which is copied here for you, we can see some pretty good information for a bunch of different equations. The first equation at the top we can tell is exothermic because it's a negative value. So if we were to write this equation, we would say carbon plus oxygen turns into CO2 by giving off 393.5 kilojoules of energy. Notice when it's written in the equation, the sign for the heat has a positive sign in front of it. It's only a negative when it discusses delta H, and that negative delta H tells us it's an exothermic reaction. So if we look at the third one down, nitrogen reacts with oxygen. Because delta H is positive, it's an endothermic reaction, so the energy term is to the left of the arrow, and after it absorbs the energy, it then turns into NO. Because delta H is positive, this is an endothermic reaction. That's it for today, so we'll see you tomorrow. Have a great night.